being here. It's a pleasure to introduce Dr. Suleiman Baraka, who is visiting us today from Calgary. He earned his PhD in magnetospheric and astrophysics from Sorbonne University in Paris, France, where he specialized in kinetic modeling and particle in cell EM3D global simulations. And then after that, he worked for several years as a senior research scientist at the National Institute of Aerospace in the US. And he's also conducted research at both the University of Calgary and the University of Alberta in Edmonton, and still maintains his affiliation with the National Institute for Aerospace, but he lives here in Canada. And it's therefore wonderful to welcome him today to CITA and hear about his work.
Thank you. Thank you, Maya. Thank you for inviting me. I am honored to be with you today. We'll start talking about the...
Let's go next one.
I think if you just tap it instead of a little game.
Like this?
Yeah, you just tap it.
Sorry, please go ahead.
So,
Is it okay?
Yeah, bigger. It's better.
okay. So once again, thanks, Maya, for inviting me and organizing this seminar. I am honored and a privilege to be with you to talk about one story of our physics community. According to David Baum, we tend to disintegrate things because we lack the power to think in theory of wholeness. So physics is physics. It's not like going to supermarket for Italian coffee, you have cappuccino, espresso, everything is coffee, so then everything is physics. Now, I'm using a code that originally started in Stanford University by Oscar Suleiman. And you cannot imagine if you start a brilliant idea, like Victor Hugo said, you can resist an army, but you cannot resist a wonderful idea and good timing. Oscar Suleiman was at Stanford University. He wanted to make a simulation to show the students how a charged particle generate around the magnetic field line. And the idea started from there. Super complicated, super complex, relativistic electrodynamics code, results of thousands of hours of best minds in Europe, United States, and Japan with this code. I am using it. It's not open source, but it can be discussed for a cooperation because still we are in 2 years and a half now modifying it to be MPI because it is not, it only uses the array in parallel, not in parallel, but we need to distribute arrays, so we save CPU time and something. This is also for good to discuss with people working in modeling. So these are the topics that I wanted to share with you today. Stop me at any time. I know we don't speak practically or technically the same language in terms of what you are doing in cosmology, astrophysics, galaxy formation, Big Bang, galaxy formation, anything about this, but this is a practical, applicable for the magnetosphere of the planet where we live and where people become technological societies. Everybody is depending on technology, civil aviation, military, telecommunication, astronauts. By the way, congratulations to Canada. We will fly the moon very soon, a Canadian and 3 Americans. We will not land in the moon, we will orbit the moon. And also this is an invitation for the young scientists that Canada is investing $300 million in a lunar gateway. So we need more Canadians to be involved in this project because now there is a trend of drifting toward moon science to make it like a space station for next going to Mars. Anyway, these are the topics I am going to discuss. So the code is kinetic, electrodynamic, relativistic. It means that there is a condition that the speed of solar wind or stellar wind cannot reach the speed of light. It's controlled. Like in quantum mechanics, you can assume speed of light 1 and you scale everything, other parameters to that speed. So the code started at Stanford University by Oscar Grunman, Kinetic Nishikawa, and Dongshun Kai. Dongshun Kai, one of the best modeler now at Tsukuba University, and he's handling ESA a simulation for kinetic modeling from Tsukuba University in Japan. He is a Chinese, he's a very nice guy, still working. Few people working in this code because this code is not compatible with the grants, you know, and having it put outside because it's time and energy consuming. So what I can share about the code called Stanford, Tri-Dimensional Stanford University, Oscar Grunman worked on that few years. And then Kenichi Nishikawa, now he quit working and that working in acceleration of celestial bodies in space. Dongshun Kai is still working. Elizabeth Wodeska from Poland worked like 15 years on that. She's retired. Spitansky in Princeton University. For the present, Ben Jaffe is our coach. He's a French. He was my PhD supervisor, and he is now the only one who is developing this version that is belonging to the Ministry of Defense in France, the CNRS and Ministry of Defense. That's why it's not open source, but it's open to cooperate. And I've been working for this like 25 years, or more than 20 years. Anyone who wants to connect with Ben Jaffe, I can give you the email at the institutional level or a personal level. As you know, kinetic modeling always working with scaling, because if you do real simulation for real world data, all computers and supercomputer facilities in the world is not enough to achieve one physical problem. So we scale, and if you are scaling, there is a price you have to pay. And there is no good or bad code. The code is relatively good if it is very consistent with the boundary condition, initial conditions, and the aim by which it was designed and structured. So kinetic modeling is, I will not say superior, because I would love always to see cooperation or coordination, not competition. Because magnetohydrodynamics is very rich in the last 45, 50 years, and hybrid coding also the same, but kinetic code has a feature that is not captured by other codes. Why? Because kinetic code can deal with backstreaming ions. In magnetohydrodynamics theory, you deal with the plasma, the star, galaxies as a fluid. Then if there is some gyration or some backstreaming, you will not see, you will not capture that. And also, you don't interfere during the run of a part of kinetic code. In magnetohydrodynamics, we change the cell size with adaptive cells. They embed some resistivity factors to add conductivity, but in this code is self-consistent. When you are okay with the physics, that the physics is not violated, you leave it until it finishes self-consistently. So the case I am going to show the results that I am writing a paper on that. The first time we had this, an idea discussed with Robert Rankin from University of Alberta, I have the sun and the moon in the same simulation books concurrently. The idea was I use my the conditions in my simulation books as an initial condition for a neuron to study the interaction between the solar wind or the plasma sheet with the moon. And was an invitation and a contract I had with GPL in California. They are looking for water and they are competing and have instrumentation sent there, and also revitalizing of old spacecraft on the moon. So people are now paying constant attentions, and billions of dollars are paid for the moon in the next 10 years up to 2030, 35, the year that we wanted to go to Mars. So there is a lot of money, a lot of work, a lot of something you can call very joyful and important and strategic for our country, that you pay attention or focus on the research of the moon. So in our code we have macroparticles. What we mean by superparticle or macroparticle in simulation, we call it PIC, particle in a cell. Each particle or pair particle, ions and electrons, in my scaling here, according to relative measuring of 100 Earth radius by 41 by 41, it's almost 1 million particles. So if I'm talking about a particle in my code, it corresponds to 1 million. That's why if you have a higher number, then you can change your Cartesian coordinate to spherical coordinates and make simulation for the Milky Way about the motion of the stars there, or the impact of the high rotational black hole at the center of the galaxy, using the same concept, the same physics, but you change these numbers and the grid sizes. So the ionospheric hydrogen and oxygen, we had IRI, ionospheric code from NASA that can liberate the upper ionosphere of hydrogen and oxygen of other heavy metals. This code, we plug it to our code, magnetospheric code. So any hydrogen, oxygen liberated, then our code is taking it according to Maxwell equations and Lorentz force law, and see how these particles escape in the vast magnetosphere. And we monitor in simulation that hydrogen reach up to 10 to 12 to 13 RE in the day side, and more than 40 RE almost reaches the moon. Yes?
Since you have such a high number of particles, do you ever incur in conditions such as load balancing problems?
Look.
Do you ever encounter, since you are using very high number of particles?
It is not very high number. It's relatively good to produce not a coherence, little bit fine structure of particle distribution.
Okay, so in the simulation, this kind of rarefact.
Yes, I will show you a paper we published in 2020. I work in a supercomputing facilities, and I have 1 billion particles. 1 billion ions and 1 billion electrons. I will tell you the story now in 2 slides. But for these particles, we derive 13 parameters, 3 components for the magnetic field, 3 components for the electric field, 2 components for the temperature, parallel and perpendicular temperature, density for ions and electrons, and we derive all the plasma parameters like the pi length, the plasma frequency. All these important are taken care of in the code. So, and the code is a little bit close to GSM coordinates, but our positive y is their negative y, which is the dawn dusk, Earth, Sun, and North, South, our coordinates in space physics. So these equations we have been working and we will be working for forever, that we use our code to accomplish here a global kinetic from solar wind to magnetic tail. In fact, the complexity of doing work like this, I'll show you a table, the variety of energy ranges, and you as astrophysicists, you can compare to your mega or tera electron volt. We are using energies from less 1 electron volt up to in radiation built few mega. So very low energy compared to what you are doing in astrophysics and cosmology. Now, I will share it's my ongoing research, that an experience that I have the moon and the sun and the earth, or the solar wind, not the sun, the solar wind in one simulation books until what I come up with. And you can see it, or you can think, if any theoretical problem that you are working on, can we use this kinetic simulation to better understand the physics? Maybe in more practical using kinetic modeling in space physics and space weather, because you cannot put in each meter a satellite around the Earth to 360 monitor the solar activities. In October 28, 2003, if you hear about the Halloween event, abrupt solar activity that jumped from 5 protons per cubic centimeter up to 8 to 1 to 100, and the speed goes to what, 800, 1,000 or 2,000 meters per second for the solar activity. What happened? This is a fact. This is monitored and was one of the alerts that for years the European, before the Americans, started the concept of space weather. And I was privileged to attend the first week in European space weather in Noordwijk, Holland. Is it a discipline? Is it a specialty? Is it part of science? Or is it a complementary something that we wanted to encounter? Now it's well established and people are working with huge number and groups in space weather. This application for space weather, what happened in October 2003, when we have this abrupt change in number of particles per cubic centimeter and hyperspeed, our current spacecraft fleets cannot capture this, and it never captured that. Because, for example, cluster European, a cluster retired last month, a cluster measure in the space energies from 32 electron volt to 40 kilo electron volt. So if you have energy beyond this range, you will not capture that. It is really very nice to working in space mission data analysis, because there is a lot of work you want to do. Even the spacecraft itself can hinder your measurements if there is a photoelectric effect on the body of the spacecraft, then it gets charges, and if it charges, then it repels more than the Dubai length, and then the probes in the spacecraft will not capture what you are going or what the spacecraft was sent to measure. So just to make a story short, when that event happened in October 20, immigrating birds, because they are using the Earth magnetic field for their directional flight, and if you see birds, always there is a leader or a guide. The fish in the ocean swim with a guide. Always there is a guide. When this solar activity hits the brain of the birds, and they lost their compass, dispersed and die. Most of the plane flying from Helsinki, from Siberia, they lost communication with the GPS for 25 minutes. Imagine a tube filled with people for 25 minutes. You don't know the direction, the height, the wind tail, no information, because every flying civil aviation is taking the information from for GPS. If the GPS hit by a solar activity abrupt, then you have people flying aimlessly and free falling. Even when I was in Holland, I saw people in the military and the Pentagon, they are using space weather, and what we are doing is to monitor the satellites that control cruise and Tomahawk missiles, because they hit caves in Afghanistan from the Mediterranean, and imagine that the GPS that control this is damaged by solar activities. This reflects how important and strategic investing in space weather. So there is a lot of, I'm slide I can't talk to it because it's my only love story and my only story for the last 2 decades. So I will go and show you. This is for you just to look about our energy in the magnetosphere. In the Earth magnetosphere, we have these energy ranges. And you, as a theoretical astrophysicist, you know what does it mean working with these ranges for ions and electrons. And imagine if you have 100, 1,000, more energetic about this, what do you need if you wanted to imply the technique of kinetic modeling for high energy astrophysics. This is very important just to give you an idea. From the magnetobose to the magnetotail, in my simulation, 100 radius RE. Imagine very small space, like 600,000 kilometers. We have these energy levels. So it's not homogeneous. It's not isotropic distribution of energies. It's very highly complex. And if you move from one layer to one layer, one energy to one energy, you either dissipate energy or supply. So that's why most of the outstanding questions in magnetospheric physics, how momentum, mass, and energy transfer, and what accelerate particles. Why do they want to know? Because they don't want to destroy their satellites, either for environment, for space exploration, for military, for espionage, for whatever reason is. So people are investing and monitoring around the second, not the hour, about any activity that can change these configurations of energy ranges. And this is like a schematic representation of the cable, just what is in where in the magnetosphere. Same thing. So for the day side, tail storage and inner response, these are the major regions that we are working to simulate, and it gives you an idea. I will leave a copy of this with the references with Maya, if you are interested to have a deeper look. So this is what I am doing now. You know, the magnetobose, if you don't hear about it, the magnetobose is the furthest shielding of the planet from the solar activity and cosmic ray, that the geomagnetic have an effect to shield us from the incoming solar wind. Typically, theoretically, for the last 60, 70 years, it's almost about 10 RE, 6,378 kilometers. Along the sun-earth line, it differs from the flank, from the sides. So people are always, in the last 40 years, they wanted to study the location, the size, and the shape of the magnetobose. In magnetohydrodynamic simulation, you see the magnetobose is well-engineered, smooth curved. But this is against the physics concept, because in physics, you have turbulence, you have storms, you have rarefaction, so it will not be a smooth curve like you are presented by magnetohydrodynamics. Very good code, like this Finnish lady, Minna Plymouth. She is a leader in Europe. She has a Flasov code, hybrid code. In Flasov hybrid code, they are dealing with electrons as only a negative battery charge, but they are not taking care, accounting for electrons. In magnetohydrodynamics, electrons are not included. In our code, we use electrons, and electrons, offset of their mass, they are very thermic. They have a high thermal speed. So their thermal speed and the momentum that they are spread when they encounter deceleration or shocks, their effect should not be negligible in our opinion. And that's what we are saying, that kinetic modeling is very important, and it's very sensitive also to very weak magnetic field and very little and very small electron or ion density. It can be taken care of by the code. That's why the cold plasma is a problem now, and there is a trend in Europe more than United States that they start working and monitoring cold plasma. Cold plasma is moving like 5 kilometers per second, which is almost the same speed of a spacecraft. So the spacecraft will never capture this, but they are huge, and they are impacting the total dynamics of the magnetosphere. That's why cold plasma, maybe if you have cold stars or galaxies or somewhere in your work, I have not updated for my work in this concept for many years. So what I wanted here to share, this figure in the left, I have a dynamic pressure that comes from the sun. The dynamic pressure, which is half rho d square of the incoming impinging plasma, and you have a thermal pressure from the anisotropy or the components of parallel and perpendicular temperature. It's not a vector quantity, but because temperature in space is measured by the velocity, by the thermal velocity, and the thermal velocity have components. So we have always we look for parallel and perpendicular temperature. When we have this incoming plasma from the sun shielded and stopped by the magnetopause, there is a balance between the geomagnetic pressure from the planet, any magnetized planet, not only Earth, and the incoming. So I saw that the total sum of thermal and dynamic, where it intersects with the magnetic field of the planet, I said this is how we measure the magnetopause size by what? By pressure balance method. So this is a technical way that we can measure where the magnetopause along the Sun-Earth line, any angular distance we can measure by this equation. Here, we typically, this curve should come to 0. Why we have it here? And that's, yeah, Maya, when I told you I sent it to David Sabit, he was in BIPOC. I said, I see a plasma inside my magnetosphere. We should not have a plasma here. And he sent me a paper that it was observed atypical events coming from reconnections or plasma slipping from the cusps where the magnetic field is weak. It's not protected, so start filling. They call it atypical events. If you have a plasma, then you have a magnetic field, so the structure completely different. And this is also accounted for, and people are paying attention to atypical events. So by this method, I measure the size of the magnetopause. If I come to this chart, we are the only people we can measure the magnetopause shape. Size you can have, we have 14 models in space physics, mathematical and statistical, they can measure that. Taking account prediction factors, there are 14. The most famous one is shown in 1997, 1998, A and B. They give you statistical model to measure the magnetopause size. But in kinetic modeling, first we transform our Cartesian coordinate to spherical coordinates to account for any planet tilt. Because if you have spherical coordinates, you better measure, or more precisely measure the shape and the distance in our box. And if you remember, this part is the plasma entered inside the magnetosphere, and this is the shape. This is the shape of the magnetopause. It is compatible with reality as it is a vibrant, not stable, it's not a wall, it's not a border, it's a high dynamic separation between magnetospheric plasma and the solar wind plasma. And this is the shape the length of this shape is compatible with observation everywhere. So we have, well, this is now I am preparing for publication, hopefully before summer. This model, we developed it in 2021. We make the maximum plasma gradient every 20 degrees in spherical coordinates in the equatorial plane. And the magnetopause is like this. So for me, it gives me a peace of mind as I am deriving the magnetopause shape in kinetic modeling. So it is shaped like this. But in that paper that we published, 2021, we made a tilt of the planet 30 degrees, just for experiment. In reality, we have 23 degrees, the planet tilt. And along that tilt, this is the tilt, and this is along the Sun-Earth line. So we can have a parabolic description of the magnetopause by this method. We offer here three planes of plasma contour for the density in the day side, up to 10 RE in the night side. This is the plasma. This is the same figure. I plotted the streamlines of the magnetic field plotted over the density, and it is exactly what my input is, because my input, I use Norton IMF. When you have Norton IMF, you are shielding and strengthening the magnetopause, because if you have a southern, then there is no correction and there is some cracks in the shielding of the planets, and some plasma can enter in the magnetopause. And this is more real because magnetic field lines are imaginary lines, but this is the plasma flow velocity. How it's dispersed, maybe the resolution is not clear. And also, it's like a supporting figures with the new figure that I showed you before. One of the important things, I don't know if you need this or you should think about this. As I told you, there is an Italian guy, Bonifazi, in 1981. He had observation of 900 hours monitoring the backstreaming ions, because backstreaming ions can come from pressure gradient, gyration around magnetic field line, or there's something in space physics called the slingshot effect. So the plasma pressuring the magnetopause, instead of going inward toward the Earth, it's split like this and moved like a slingshot. And when the magnetic field line making a slingshot attack, it takes particles blood. So you have a sudden acceleration of particles resulting from dynamic pressure if you have a compression. So Bonifazi, what he did, I am adopting his theory from here. So I went and singled out only backstreaming ions. You can imagine if you see something counter moving in galaxy formation or whatever you see, or in nebula and whatever. And he said, if we measure the velocity of the backstreaming and measure its thermal velocity, if the ratio is 1.2, so the backstreaming is reflection. And you can assume what the reflection comes from. But if this ratio is less than 0.8, then you have diffusion. In between, you have intermediate. This is very important result, I think. And I recommend, if it's okay for your work, to pay attention for that, because even in kinetic modeling, if you ignore the backstreaming ions or galaxies or stars impact, then you are not showing the real physics or the true physics or the precise physics. Because what you see is the magnetohydrodynamics. So the magnetohydrodynamics, the backstreaming is included. But if you single them out, then you know the true kinetic impact of the stream. And that's why you can correctly understand or study the shocks, the solar storms, the magnetic reconnection, which is a very, very, very hot topic in the space community. This important also issue for the temperature anisotropy. Our code can easily calculate from the binary data the temperature anisotropy. And temperature anisotropy, then you have disturbance in the flow and dynamics, and then you have potentially have breaking the quasi-neutrality of a plasma. And if you break the quasi-neutrality of a plasma, then you have a charge separation. If you have a charge separation, then you have a potential. If you have potential, then you have induced electric field. And this electric field, you don't account it for the solution of Maxwell equation, but it pops up as a result of that interaction, which is very important also results, in my humble opinion. So the second part of this study, we used international ionospheric code from NASA. We took the oxygen and hydrogen at 1.2 RE, and we did with our calculation in our code. It's only a test for oxygen and hydrogen liberated from the upper boundary of the ionosphere. 5 years, we discovered that the code from NASA there is a mistake because underestimate the rate of oxygen by 50 times. So if IRI model show that you have 10 particles of oxygen, it is 500 particles in fact. And this is have a huge impact on the dynamics and the structure of the macro structure of the magnitude. So in this code, I use okay. This is also very good information. So when you have oxygen and hydrogen liberated from the ionosphere, liberated means goes against gravity. Oxygen is very heavy. So there is a Jeans model, Jeans escape model, and Jeans is statistically means the square of the escape velocity over the thermal velocity. If it is less than 1, then particles can not affected by the gravity, and they have enough thermal energy to go. We find that it is not the thermal velocity that the liberated oxygen and hydrogen. We find it the open magnetic field line gyration, which is this is how the beautiful the code is. So even at that level of statistics, we can characterize if this liberated or escape particle from the ionosphere is it as a result of Jeans escape factor. It means that they have thermal energy more than the escape velocity, or it is gyrated and was able to combat with the gravity and liberated from the gravity. When it is liberated from the gravity, it will be controlled by the dynamics of the magnetosphere and the Maxwell equations inside the magnetosphere. Here I show, this is the model if you wanted to have some critical information. Here I show a two-dimensional distribution of ions and oxygen, the left for hydrogen and the right for oxygen in a 3-dimension, in XZ plane, sun-earth line, and dawn dusk in the equatorial plane and north-south, and see the distribution comes up to the velocity this is the velocity, but also the linear representation can go up to 13 in the day side and 30, 40, even 60 for the hydrogen RE. This is also an idea how the liberated oxygen and hydrogen can be simulated by kinetic modeling. And the people in GPL are interested if the hydrogen and oxygen have enough energy and reach the surface of the moon. And we make ionization coding for them. Can be they a source of water? Because one of the answers to the problem in the moon, the source of the water in the moon is from comets. But the quantity of water is very much bigger than the calculated comets bombardment of the moon. So there is another source that we are looking for. In GPL especially, they are investing, they are a large group. They wanted to know what else can contribute to the production of water on the surface of the moon. And also, they say it's observed that the water migrated from the equator of the moon to the poles, south and north poles. Also, they wanted to know what drives them there. Especially the regolith, the soil of the moon, is highly complex, and it's not magnetized like the planet, but the excessive accumulation of charged particles bombing it creates a mini magnetosphere. So some part of the surface of the moon repels impinging solar wind or plasma density particles. This is the same thing for ions and electrons distribution, velocity distribution function for the ionospheric magnetospheric coupling. So I will move directly to the moon. This is my map. The case I gave is a special case. My case in simulation, my moon is here. In here, plus minus this, it stayed at 20% of its orbital time in this area. In this area, you don't have a solar wind, you have a plasma sheet, some of which ionospheric and some of them from the solar wind. It's a very low density and very complex. So my special case here, this is the from line in Nature 2023, and this is the characteristics of distances about the dome dust asymmetry of the moon. I use this as a base and a reference, and then I made an assumption. I know that solar wind or plasma hit the moon is absorbed. And my assumption in this solution, let me assume that the moon is a physical obstacle. Why I did this? I said how much accumulated plasma, if I stop it at the angular distance of the moon, then I can calculate the amount of plasma absorbed by the moon. And my surprise that here we have a breaking of the quasi-neutrality. So ions are dominating in the lit side of the moon and electrons are dominating in the dark, which is observed. So when you see the full moon like today is the full moon. The full moon is positively charged and the dark side of the moon is negatively charged. There are some observations that vice versa, but typically this is the case. In my simulation, to my surprise, I find the same result here. And also, as I told you before, when you have this encounter, you come up with this figure. There is induced electric field in the moon. So if you are only looking for the solution of Maxwell equation in the book to measure your electric field, you don't have the effective electric field because there is induced one, and this induced one is related to the mass and velocity and the plasma frequency of electrons. This has an impact. It is like 1 millivolt per meter, but it's still very effective at that low density. It can disperse. And you cannot, if you don't account for induced electric field, where you can capture only by kinetic modeling, then you miss important measurements in total evaluation of the physics of the day-side moon as seen in this figure. So I also, this is to show you how we can apply it in many things. Our code. This is really important for you. This paper I contributed in 2022 with a very large number of people, 77 pages. This figure, plasma distribution and magnetic field topology of an exoplanet orbit within the corona of its parent star. Because our code is written by Fortran 77, old-fashioned like myself, and cannot be changed easily. It's very costly. Most of the submarine and models and in NASA is still written in 77, and they cannot even, we have 1 million new, in new languages, they still have Fortran 77. And I like it because I was in sixth grade that time. So I feel it has something to do with my childhood. And the structure of this French code is not MPI, it's not, the arrays is not distributed into different arrays, so you have to save time. This figure, believe it or not, I spent 800 hours in a supercomputer at Hampton University to finish this. Why? Because I use 1 billion particles for ions and 1 billion particles for electrons. And imagine this is a macro particles. If one particle is 100 in real particles, then you can simulate the Milky Way, 100 billion stars. And any star you consider like a dot or a particle, and you can simulate. So this is, if you have, I think you have supercomputing facilities at the University of Toronto. 800 hours, if we can move it to MPI, it could be 20 or 30 hours. The figures I showed you, I made the simulation in France in our computer in the Institute of Astrophysics. It takes 1 week. Every single file, 3.6 gigabyte. So the mass ratio between I is 100, and we have 1 billion particles. This is published in 2020 with Gronov, and this was my contribution in that paper. This is my Lutfi bin Jafar, the code that was published in Nature. This code also employed the same code in Exoplanet. Of course, he had, the Jupiter moons, they are magnetized like planets. And they find that the impact of this IO or Europe, they have magnetic field that make a cavity in the atmosphere of the planet. Also, they use this. And also, Lutfi made a paper in Nature with a Polish guy, Polish team, and American team. Also, they simulated image satellites about Saturn. So this is, I give you example without any details that this code is highly applicable in many magnetized planets or non-magnetized planets. Next step for our development is to use the planet for the neutral atoms. Because if there is charge exchange or neutralization, then our code will not see it. So we wanted to include the neutral atoms because the neutral atoms, particles under chemistry is not included yet. This is a paper published now. Application to national Canadian space projects. I suggested that, unfortunately, I didn't succeed to have the right networking to employ my expertise to help or to contribute, not to help. There are two major national projects for Canada: SMILE, which is solar magnetosphere, ionosphere link explorer. This is a Chinese European Space Agency project, but Canada is contributing for that project. And they wanted to measure the magnetopause that I showed you by X-ray imaging. And if you use X-ray imaging and you don't have enough particles as a background, you will not capture that. But our code can do that. That's why I proposed the University of Calgary said, nobody can do the job except you. I wanted to, because we signed a contract with the space agency in Europe. I said, okay, I'm here. I'm 10 minutes to drive. And then a few weeks, I said, oh, sorry, there is a cut of $400,000 from Canadian Space Agency. We cannot give you the job. This is what I offered and agreed with people like Robert Duncan and other people working in SMILE projects, Andy Samsonov, even Eric Donovan from Canada. a very large number of British working in this European Chinese project. So this is a SMILE project. And this book, not me, anyone who's kinetic modeling can be a good fit to help those guys if they have a bloody imaging. This code can verify if it's real or not because of the ability of the code to deal with very low magnetic field and very low density. So this table showed you how this SMILE problems can be solved by magnetic. It's not a big deal for you, but I leave a copy for you if you are interested to study. SMILE, you get to know as a Canadian that this project is for your country, is contributing, is very important. And then NASA Gateway Project. This is what I told you, Canada is investing $300 million in the next 30 years in this project. And CSA, I saw many appeal that you need to write a proposal and try to contribute to this. Canada is, this project is contributed by industry in the Lunar Gateway. Because in Lunar Gateway, they will not land in the moon. They wanted to build a station to be a background to move to, in this economic feasible, to Mars later on. So this is very important project. Also, we can create this code. I don't want to see subjective things. This code can help in these two projects. So this is a summary of what we can do or what the code can do for national projects in Canada. And this is our references. Then to see the research. What I am talking here, what we can work together, and what ideas need to be discussed. And we can we find a common research background that we cooperate. This is what I can share in this regard for the link between kinetic modeling of a specific plasma. I give you examples about magnetospheric physics. I give you example about simulation of large planets, moons like Jupiter and Saturn. I give you example about supersonic and hypersonic speedy exoplanets. I myself contributed to paper and also 3 or 4 papers published in this regard at the same point. So this also a contribution from Ben Zafir. And here is my conclusion for this talk for today. Institute of Astrophysics big code is highly versatile, can be applied in very low energy motion of particles and very high energy depending on the scaling factor. And it could be a common background, a common ground that we cooperate together and work for the betterment of our physics community and also for the strategic projects that protect our airborne properties and ourselves, because we are a little bit in the north, in the latitude that can be attacked by solar activity. It happened in 2023, damaged satellites and birds, and thank God that no accident in the plane. 25 minutes lost in the space with 800 or 900 kilometers per hour is not. It's not a game. It's very scary, and also making this simulation. It is physics central and physics principle central work, because the mechanism of updating fields in the code is Maxwell equation with well-established theories and laws, and the advancement of particles is Lorentz force law with a relativistic speed, classical speed, everything is discovered. So I wish that I will have 100, 200 people working on the same thing. We can solve millions of problems. Unfortunately, I was working for the last 4 or 5 years for National Institute of Aerospace at Hampton, which is NASA for non-US citizen, because we cannot go inside the gate. I was working there, but I kept my contract with them. And I worked 2 years with the GPL about the moon dynamics of interactions. The thing that I showed you in the moon is in the tail, in the line, the sun earth line. But the other way we wanted to simulate is when the moon in the solar wind, 60 RE in the solar wind, before the solar wind reaches, it's another physics, very important. I don't have the time, I don't have the population, I don't have any even work that I invested somewhere to see the interactions of the solar wind before coming to the planet, which is the new moon phase, when the moon is between Earth and Sun. And here is my talk, and I am very open for questions, and thank you very much for your attention.
Maybe one question before moving to the discussion.
Yeah, so you mentioned about the water on the moon and that being from due to the ionization and bunch. Is that enough flux of those ions to sort of actually create the water in the required quantities?
This is the question the CPL did me for 2 years to understand if the solar wind or the ionospheric scaled ions is energetic enough to ionize and make water. They still, to the best of my knowledge, I don't know, in the last few months, if there is something published about you find another reason. That's why we're sending spacecraft. As I told you, it's very complex. Even when I start studying the moon, it's very complex, the moon environment. They call it absorb these charged particles, and suddenly it becomes a little bit like a mini charge and start blocking the impinging solar wind or plasma. But every one, let's say, kilometer in the moon is not like the adjacent other kilometer if there is some ridges or mountains or heights, because there is a shadow or chorus, or the friction or the roughness of the rebellion, and the shadow in the moon is making other physics. That's why, for me, the very minimum distance by my code, I reach 170 kilometers above the surface, which is enough to see if I can deliver oxygen and hydrogen there. But I cannot reach less than 170 kilometers, which is almost 1/10 of the moon radius. Moon radius is 1720 kilometers. So the minimum my code can reach there is 1/10 of the radius above the surface of the moon, which is important. We have spacecraft, we have astronauts, we have many things. So also even the information that offer about the induced electric field, the magnetic field, the deflection of particles is also very important for paving a safe pathway for spacecraft and astronauts if they reach that distance.
Yeah, let's thank Suleiman again. Okay. Oh, with the